Hi everyone, and thanks for joining us today for this webinar. We will go ahead and get started right away since there is a lot of material to cover today. We're going to really be talking about the basics of functional safety. So safety instrumented system and safety instrumented function, basically the 101, how things started and began. My name is Loren Stewart. I am a CFSE. I work here at exida. I predominantly work with our mechanical customers. I do the trainings. I go on site or do open enrollment trainings, as well as work with some of our end user customers. exida, we are a worldwide company, so no matter where products get certified or where they get used or where you are, we have someone close by to help with any functional safety needs. We have functional safety or process safety, alarm management, and cybersecurity people and tools to help you out. We cover the complete supply chain of functional safety, so whether it's the OEM that needs their product certified, the whole way through to the end user who uses those certified products, and the people that help make those happen. We have tools and services to help anything to do with functional safety. As I said, we have engineers and consulting services in functional safety or process safety, alarm management, and cybersecurity. Our tools were really designed to help you save time and money, and they do that by increasing efficiency and productivity. We have tools that can help with PHAs, LOPAs, cell selection, cell verification, to create your proof test procedures and your SRS, your cyber risk assessment, alarm rationalization, something we called the Site Safety Index, which we'll talk a little bit about today. And we're going to also look at one of the tools that we have, but we have engineering tools to help you in your functional safety needs. We're also going to speak a little bit today on certification, and exida has a certification portion of our business, and we certify to IEC 61508 and 511, ISO 26262. We have ISA Secure, or the cybersecurity certification, machine safety, and personnel certification. In our functional safety certification, or a special look at IEC 61508 and 511 today, how they came about, why there's a need, and so we're going to start with that. But let's get into it. As I said, we have so much to cover, so I tried to quickly go through that. Hopefully, if you want more information on exida, you can visit our website. So, last week, I was at a major OEM educational conference, and I did a speech. I actually did a workshop. It was 90 minutes long, and it was well received. We had a lot of people come up to the booth afterwards. They said how much they enjoyed it, how much they learned. We had people talking that they wanted more. They wish they had colleagues that were able to see it. So I decided to take that 90-minute speech, shorten it down, and create a webinar. We did this, both the speech and the webinar, just because we really know that the standards on functional safety really can be lengthy. If you print them out, they're going to be inches and inches thick. They can be difficult to navigate and understand. The wording is in all of the shoulds and the shalls. So it's not always the simplest task to take on when you are looking to get more information on functional safety. So this webinar is really to help unravel some of those mysteries behind safety and help navigate the user through the standards, through the requirements, what's really important. Hopefully you're going to take this subject and you'll learn a little bit from it today. We're going to talk about numerous different topics just briefly, but hopefully you take away some things such as the terms we're going to use in functional safety. We're going to talk about proof testing and maintenance, and hopefully you'll be able to take a little bit away on those key topics. But as I said, today we're going to go over basic functional safety fundamental requirements of IEC 61511 and 508. We're going to talk about PFDavg, or probability of failure on demand, and get more information on functional safety. As I said before, we are going to cover a lot of topics, and unfortunately we can't dive very deep into any of them today because I'm trying to keep it down to an hour. So if we touch on anything and you want more information on it, we have great resources on the exida website. All of these subjects have their own webinars devoted just to those topics. So if you want more information on proof testing, we have webinars on proof testing. If you want more information on systematic capability, we have webinars and blogs on that as well. So if you want any information on any of the topics, go back to our website, go to our recorded webinars, and you can view all of those. But today we are going to break the agenda out into three main sections. We're going to talk about why functional safety is important, the design and maintenance of safety instrumented systems, and then what safety culture comes into play and how that comes into play. So we're going to start with who cares? Why our safety systems are important. Well, they're really to prevent some serious and potentially deadly disasters from happening. These are just two examples. There are examples happening every year. These two happened in 2005. They are some of the more well-known disasters. The first is a refinery explosion happened in Texas, and a hydrocarbon vapor cloud appeared and found ignition and killed 15 people and injured 170. That same year, there was a fire at a storage facility in the UK, and 40 people were injured. The good news, if I could say there's any good news from these, is the one in the UK happened very, very early on a Sunday morning, something like 4 a.m. I believe it was, on a Sunday morning. And because of that, there weren't many people at the facility. Because if it happened during a normal work period or work day, those numbers would certainly be higher. So when it comes down to the end of the day, functional safety is really about reducing personal risk to the environment, and financial risk. So functional safety is not just about reducing people dying or people being injured. It also takes into consideration the environment and financial risk, business interruption, fines, litigation, all of that plays a part. So functional safety, as we just mentioned, is how you can reduce risk. And when we are talking about reducing risks, in IEC 61508 and 511, it mentions to reduce risk as low as reasonably practical or possible, depending who you talk to. And this concept is called ALARP. And ALARP is taking a risk that happened all too often, or is intolerable, as such as an explosion that multiple deaths would occur, and reducing that risk until it's in the broadly acceptable, or we accept it, the general population accepts it region. So as this graph shows, there are some things that we normally accept risk as a general population. When it rains, I still walk outside. I know there is a possibility I could get struck by lightning, but if it's not a horrific storm, I'll usually run outside from my house to get to my car, or vice versa. Just as a plane ride, I know that there is a chance that a plane can crash. Crashes happen, but I still went to this conference. I got on a plane and I accepted that risk. Something like smoking. We now know how dangerous smoking is for your health, and most people have decided that the benefits of smoking, why people smoke, isn't worth the risk. So that would be something that would not be tolerable. So you have your event and that risk associated with that event, and you want to lower the risk as much as possible. Somebody will always ask me, well, I want to get rid of all risks. I want it down to 0 risk. And I simply tell them, well, don't open up your plant. Even constructing the plant, walking to the plant, anything you do is going to have some sort of risk associated with it. So if you want 0 risk at all, there is simply no way to operate. But it is a great thing to lower your risk as much as possible and get it into that broadly acceptable, or that green area. So now we know functional safety is a good thing. Functional safety is probably pretty needed in a lot of areas. So what is the actual goal of functional safety? Well, IEC 61508 and 511 define functional safety as the automatic safety function will perform the intended function correctly, or the system will fail in a predictable or safe manner. So what that means is that a bad thing can still occur as long as an automatic safety function can make the system fail in a predictable or a safe manner. We talked a little bit already about the standards. You've heard me refer to them as IEC 61508 and 511. Well, IEC 61508 started by a group of people from around the world, got together, wanted to create something for functional safety, a standard that applies to everything. And it was created, IEC 61508. It's referred to as the umbrella standard, or the grandfather standard. It's what really got functional safety going. After that was put in place, people figured out you needed more industry-specific standards. So then sector standards were produced, such as we have the nuclear sector, we have a machinery, and then came the process industry sector. So if you are an end user using certified products, building your system, you're going to be referring to the rules in IEC 61511 in the process industry sector. However, you are using the certified products that apply to the suppliers that use IEC 61508. So there are portions of where the standards overlap and they agree with each other, and sometimes they reference each other and say, go back to IEC 61508 for this or for that. But for the most part, you will be buying certified products that were made from 508 and applying them using the standards of 511. In both IEC 61508 and 511, there's a thing described as a safety integrity level, and you might hear it as a SIL level or a SIL rating. There are 4 SIL levels, 1 through 4, 1 being the lowest and 4 being the highest, meaning it can reduce the most risk. It also means it was probably the highest risk to begin with. So that SIL 4 has the most requirements, where SIL 1 has the least. If you have a SIL 2 rated product, you have a product that met all of the requirements for SIL 1, plus the requirements needed for SIL 2, and on up. And these 4 SIL levels are really defining how well your safety function performs its job of managing risk. Just to note, in the process industry, you'll hear of really SIL 1, 2, and SIL 3, whereas SIL 4 is mostly saved for something in nuclear or sometimes the rail industry. SIL 4 in the process industry is normally thought upon as kind of a unicorn or something that, well, we all know it exists, but has anyone really seen it? So what do you do? How are these SIL levels used? Why are they important? What goes into it? Well, to say your safety function is SIL compliant, you need to overcome 3 hurdles or 3 barriers to overcome. And those are SIL capability, architectural constraints, and probability of failure. And we're going to look briefly at all 3 of these, and like I said, if you want more information, all of these have their own webinar. There's also a webinar on how all 3 compliance with all 3 met together, called the 3 barriers. There's a lot of information out there, but today we'll just go quickly because we have so much to cover. Anyway, no matter how well you do 1 or maybe 2 of these categories, say you do 2 of them perfectly, but you're not considering the 3rd barrier or the 3rd hurdle, it really doesn't matter. You're not in compliance with the standard. So when you are putting together your SIF or your SIS, there are really 3 things that you need to consider. And let's look first at the systematic capability and what that means. So if you buy a certified product, you have your certificate. This is what is on the certificate. You might see the words, if it's an exida certificate, you might see the words systematic capability or SIL 3 capable or SIL 2 capable. That talks about really the quality management system of the manufacturer of the product. When you are buying a certified product that was done by a 3rd party, they had someone come in, evaluate the product, evaluate their quality management systems. If it's been in the field, look at their returns, look at, this really is focusing on how they make modifications, if there's an impact analysis. This is looking at their safety manuals and their IOMs, how they deal with returns, how they do new products and procedures. That's what systematic capability is. And when you have a certified product, the capability or systematic capability is as high as they can go. So if you have a certificate for SIL 2 capable, it can go in a SIL 2 or a SIL 1 or no SIL level SIF. However, if you cannot use that product in a SIL 3 SIF. So that is the highest that the product could be capable of going. So that is your systematic capability. Next is our architectural constraints. Architectural constraints can be known as architectural constraints or redundancy, hardware fault tolerance, minimum hardware redundancy requirements. All of that is the same. It's barrier 2. Or if you've heard of Route 1H or Route 2H, that's directly from the standards themselves. Well, 1H is a safe failure fraction. It's looking at the ratio of the average rate of safe failures plus the dangerous detected failures of the subsystem to the total average failure rate for the subsystem, so the safe and the dangerous. And that's done for a single channel, so no redundancy, so a 1 out of 1 product. Or Route 2H, that is more of a proven in use type application. You're very highly confident, greater than 90% confident on your data set and your data collection. You go down to root cause analysis, all of that information. So that is Route 2H. As I said, the architectural constraints are applied to the elements separate. An element meaning your final element, your valve, actuator, and solenoid together. So if you have just a valve, you can't do your architectural constraints on just your valve. You need your whole final element or your subsystem to do your architectural constraints with. Barrier 2 was really in place to protect against people using and abusing barrier 3, which we will get to in a second. Barrier 2 has tables in the standard, both in 08 and 511 standards. This is the one for Route 1H, and so it uses the safe failure fraction. And to use this table, if you have a simple loop such as a valve actuator solenoid with a safe failure fraction below 60, if you have calculated you need to have at least SIL2 risk reduction, that means you have a hardware fault tolerance of 1. Well, what's that? Hardware fault tolerance is how many extra sets you have, how much extra redundancy is in place. So for a SIL2 application, less than 60% safe failure fraction, you're going to need 1 extra set of equipment, such as a 1 out of 2 or a 2 out of 3 SIF. As I said, barrier 2 is put into place to prevent people from cheating at barrier 3. And barrier 3 is the probability of failure. Well, what's that? Have you heard of probability of failure on demand, or PFDavg, or average probability of failure on demand? That all is talking about the probability of failure in low demand mode of operation. If you've ever heard of PFH, or probability of failures per hour, that's actually the same thing, but looking at it as a high demand mode of operation. The PFDavg is based on your dangerous failure rate. It uses other things such as diagnostics, proof test coverage, test intervals, mission time. All of that information goes into the equation for your PFDavg calculation. And where people cheat is having unrealistic failure rates, unrealistically low dangerous failure rates, and then this your probability of failure on demand is saying that you're not going to have, your valve is not going to have a failure for 10,000 years. Okay, so that's why architectural constraints are in place. However, it in itself is a barrier that you need to meet as well. Typically, if you look at your final element assembly, so your valve, your actuator, and your solenoid put together, they're not smart devices, so there's no really ways for them to fail safely on their own, that automatic diagnostics. So usually the PFDavg for your final elements only meets SIL 1. However, there's things that you can do to improve your PFDavg to a SIL 2 per se, such as doing your proof test more often or shortening the mission time. And there's webinars just on the PFDavg calculation and all of the variables for that if you want more information. Now we're going to move over into maintaining and designing your safety instrumented system. And we're really going to focus on that PFDavg barrier right now. There are 9 key variables in the PFDavg calculation. They are failure rates for the product, which is really designed into the product. You can get that by buying certified products. Anything that's had an FMEDA done will have failure rates. Next variable is your architectural. If there's any redundancy, if you're considering common cause, all of that is the next variable in the PFDavg, which is something that you as an end user control. The next variable is your proof test interval. This is, once again, controlled by you, the end user, along with your mean time to restore. So when there's a failure, how often or how long since the failure for you to be notified to getting back up and running. We're going to talk about proof testing and proof test effectiveness coming up. The mission time, how long your piece of equipment is going to be in the field for. Is it a 5-year mission time, a 10-year mission time? What do you need this to be? A 1-year mission time? Once again, that's something that you can control. Proof testing, if you do it online or during a shutdown, if there's bypass, how long the proof test duration is going to be if it is done online. Those are things that you, again, as an end user control. And then finally, operation and maintenance capability. This is how well you do your operation and maintenance as an end user. So once again, you control that. So if you have an OEM that is giving you a PFDavg number on just their valve, there's a lot of variables that they're making assumptions with. And as a functional safety consultant, I highly recommend you doing your PFDavg calculations yourself, because you know what these variables actually are going to be, and that way you'll have a much more realistic notion on what your average probability of failure on demand is. So if we're going to talk about proof testing, proof test design, proof test coverage, all of that information, it's best to know what we are considering a proof test to be. So proof test is defined by the standard IEC 61508 as a manual periodic test performed to detect dangerous hidden failures in a safety-related system, so that if necessary, a repair can restore the system to an as-new condition, or as close to that as-new condition as possible. Exida took that definition and took it a few steps further. We said the purpose of a proof test is to detect any of those failures not detected by automatic online diagnostics. That being dangerous failures, diagnostic failures, parametric failures, and any detect unauthorized program changes. Why is that? Well, if you're already having automatic online diagnostics running, why are you going to do a proof test confirming the same thing. That's just wasting your time and wasting your money. Design your proof tests around what your automatic online diagnostics are not telling you. When you are designing your proof test, you need to consider what the functional requirements are and what the performance requirements are. Functionally, what do you need your safety instrumented function to do? What do you need its function to do for you? The performance. You need to consider those requirements as well. Are you allowing any leakage or not? Are there any timing requirements or not? So for example, you have a final element. Say it's a close on trip application, your functional. It needs to close to IEC 60534 class 3 leakage, and it needs to do so within 180 seconds. So that's how you combined your functional and your performance requirements. When you are designing this, you need to make sure all of the equipment that you're putting in there, that it does not violate any exceptions written in the functional safety manual of each product. If there are any exceptions to the certificates, they would be listed there. So if you are designing your proof test, you're obviously going to design the best proof test possible. You're going to design the perfect proof test. So on our graph here, let me get a little highlighter or laser pointer. As time goes on, your probability of failure increases. So as time increases, the chances of a failure increase and increase and increase until you decide, oh, it's time to do a proof test. Well, at that point, you do a proof test. You know that you checked for all of these failures. If they're not there, there's no probability of a failure. So you go down to 0. And then you start the cycle over again until another proof test, back to 0. For the lifetime of the piece of equipment. When you are talking about a low demand application, you are then talking about a PFD average. Because you do not know when in this curve demand may happen, you need to take the average. It could happen at this point, it could happen at this point. So you in turn, the standard says you take the average of the PFD, and that is your probability of failure on demand for a low demand application. Why do I keep on talking about the perfect proof test? Well, what's not perfect? Say I run a functional test and see the system respond, then everything we needs to work, it works. That's perfect, right? What's the problem? Well, is everything really tested? Let's say you take a pressure sensor and you isolate it and the pump such that the sensor pressure exceeds that whatever trip point it is. The remote actuated valve, it's observed, it moves. It's perfect. Everything's tested, right? Well, the seals of the valve, you didn't check for any leakage, so you don't know if the valve is leaking or if the valve seals properly. Okay. If you didn't record the response time, you don't know if you have a component that's failed or even if it's just degraded. That may be slowing the response time of your process, and that in turns exceeds the timing, exceeds the process safety time. Okay, that might be another problem. What about If you have a power supply droop or a wire resistant, and it may be limiting maximum current, disabling diagnostic alarms. You get my point. Not everything's going to be tested, no matter how well you try and do your proof test. So, proof test coverage is introduced because of that imperfect proof test. A proof test coverage is going to be this portion. Let me get my laser back. Anyway, it will be the C of P sub C sub P of T. And that is going to be a percentage on how effective your proof test actually is. It's going to be between 0 and 100%. And it's going to be calculated for the entire lifetime of the plant or lifetime of the SIF. So your first time, as time goes on, once again, your probability of failure is increasing, at which point you decide to do a proof test. You, being a realistic person, realize you're not going to test everything. So your proof test is very good, but not perfect, and you're saying, oh, it's 60%, or it's 70%, or it's 80%. So here is the effectiveness. It drops down, and then you have your new starting point from where your probability of failure starts. And if this might not be a big deal if you have 1 or 2 mission time or proof tests per your mission time, but what if you have 5? What if you have 10? That's where you start getting into trouble. Because it's never perfect, and your SIL is showing how much risk you are reducing and how well your SIF is going to respond to a failure, you could be running at a slightly or a significantly lower quality and higher risk. So here's an example. Your first year, you've done all of your calculation. Well, I know for a fact I am operating in a SIL 3 range. And that might be true for your first year. If you assume perfect proof test, you're going to be in a nice, warm, and fuzzy area thinking that you're always in SIL 3. However, being a realist, you're actually not. So you're not finding every dangerous undetected failure. So the next year, it increases, but you're still in SIL 3. That's okay. However, year 3, all of a sudden you're operating in a SIL 2 range. What about year 5 or year 6? You might actually be dropping to a SIL 1, and you never want to be underestimating when it comes to safety. So let's put real numbers. I like examples. Let's put some real numbers to this. And consider a high-level protection SIF. It's designed with a SIL 3 certified level transmitter, a SIL 3 certified logic solver, a remote actuated valve that's certified solenoid valve, certified actuator, certified ball valve. Your mission time's 5 years. Your proof test interval is going to be 1 year for your sensors and your final elements and 5 years for your logic solver. You're going to assume that your proof test coverage is 100%. It's always going to be 100. You're just going to leave it at that and just do your calculations. Your proof tests are going to be done with the process offline. So in this example, here's a screenshot of exSilentia, one of our tools if you haven't seen it yet. And this is showing that you have for your sensor, your logic solver, oh, there's my laser pointer back. Your sensor, your logic solver and your final element, you're going to have a probability of failure on demand, your average, since it's low demand mode for each. You have to pick your weakest link, and it shows that for your CIF, you're going to have a PFDavg of a SIL 2. This is also coming with a risk reduction factor of 147. Okay, great. So now we know where we stand. Let's take everything the same, except let's do a proof test coverage of 90% for your sensors, because that's average for a sensor, and 70% for your final elements. And this time you're going to do your proof test online with a duration of 2 hours. So now your PFDavg, you once again have it for your sensor, your final element, and your logic solver. But now you have a PFDavg for your SIL as a SIL 1 rating. Uh-oh. And now you look how much risk you have. You only had a risk reduction of 17. What if you needed in your SIL calcs a risk reduction of 150 or 100? And you were meeting it previously, but now you're only at a risk reduction of 17. What if you're not making it anymore? And these are real life numbers. This is actually could happen. So now you know, how is your proof test effectiveness measured? Well, proof test effectiveness, once we talked about, is a range. It's going to be your percentage. It could be 0 to 100, but typically you're going to be in a more 40 to 90% range. And it's a percentage of your dangerous undetected failures. Once again, manual proof tests are done to detect failures not detected by danger or automatic diagnostics. If you are comparing two products that are similar, and you see one that has better automatic diagnostics, it will usually show up as a lower manual proof test number, and I'll show you an example coming up about that. So how do you determine proof test and your proof test effectiveness? Well, proof test effectiveness, if you buy a certified product, it will be in the product's safety manual and the product's FMEDA. This is required by IEC 61508. This is an example of a proof test. This is a very comprehensive example because they give you multiple different ways of doing a proof test. You have your partial proof test. It checks a few things, but it's great because you do not have to remove the process from the device from process, but you're going to have a low proof test coverage. On the other hand, you're going to have a comprehensive proof test that you remove the device from the process, but you're going to find 99% of potential failures. It's going to do everything the original proof test did, plus verification, plus an inspection, plus calibration. So as you can see, there's a lot more work to do there. And then they actually go as far as giving you somewhere in between. Why does a company do this? Well, maybe pulling your device from process isn't going to be easy for you. Maybe you can only do it every so often. So you do your partial proof tests more often to delay that comprehensive proof test. Anyway, as you can see, you have your 3 proof test effectiveness here. There are going to be steps involved on how to achieve these with every proof test. Let's look at another example. So let's take 2 separate products this time. Let's say they are both some sort of subsystem or system or element. They both, different companies, but they both have the same dangerous failure rate, just to make our math easy for us, of 100 fits. If you're not aware, a fit is a failure in time. It is a unit of measure that the standard uses and functional safety uses often. They are expressed in 10 to the negative 9. And if you look on the back of a certificate of a certified product, it's expressed in fits. So you have two products. They both have dangerous failure rates of 100 fits. The first product has, from company A, has poor automatic diagnostics. So you have approved test coverage of 80%. There's a second product, maybe from company B, who has very similar but has good automatic diagnostics with approved test coverage of 20%. So we get asked, well, which product is more safe or more reliable? Which product would you purchase? Well, don't rely on just your proof test coverage to make this decision for you. So company A, they have that poor automatic diagnostics, so they only detect 10 of the 100 dangerous fits, leaving 90 fits still undetected. So those are 90 potentially still undetected dangerous failures. Your manual proof test detects 72 of those remaining 90 dangerous fits. So your proof test coverage is 80%. That leaves you 18 fits still undetected. Company B, however, the one that has good automatic diagnostics, they find all but 10 of those fits. Their manual proof test coverage is only 20% because they only find 2 of the remaining 10 fits. But the bottom line is how many were left still undetected? You have 18 fits compared to 8. So never use proof test coverage as your measure of quality for a product. Almost the opposite is sometimes true. So how do you determine this proof test effectiveness? Well, you can establish a baseline failure rate for the device. You can perform an FMEDA with a credible database, assign coverage as a function of failure mode and by the test, allocate between diagnostics and proof tests, or if you are the company that manufactures this, you might be able to do that for yourself. If you are an end user using this product, that's probably going to be quite difficult for you to do on your own. Or you can surpass, or just get rid of all of that, not use it, and actually use data from the certificates from a third-party certification. It will be that proof test effectiveness in the FMEDA and as well in a safety manual. So quickly, we are going to now look at safety culture. Now we know how important our SIF is, why we have our safety function in place, how important it is. How important is it now to maintain that and to keep that safety culture? Well, without having a proper safety culture in place at a site, really having certified products won't matter. Doing your calculations perfectly won't matter. Having the best equipment money can buy, it won't matter. Safety culture encompasses repair, doing it imperfectly, human factors such as improper calibration or faulty installation, not doing your proof tests on time or repairs on time, and all of these things can contribute to a decrease in the performance of your SIF. Site Safety Index is a model that's used based on all of the approaches from IEC 61508 and 511 that can adjust the safety metrics that are computed to let human factors play no part in the safety performance systems. When you are doing your calculations, these type of failures contributed by humans don't come into play into calculations. So how do you not mask one company, let alone one site, covering up for bad sites practices? And you might be wondering why I'm saying site instead of company. It's because we were seeing the same device used by the same company and different failures and number of failures coming back from all of their different sites or locations. We wanted to know why. It's because each site was interpreting their global procedures differently. Let's say site A was very strict. They made sure their calibrations and proof tests and everything were happening on time and when they were supposed to. Where site B was more relaxed. We really tried hard to get to it this month, but it's just not going to happen. Next month, we're going to push it. Or to some sites, site C, what? You have maintenance? Anyway, we did not want to punish site A for the things site B and site C were doing. So if you can prove that you have wonderful site safety, you can take credit for that and not be punished by your counterparts. So, and Site Safety Index model is built into exSilentia. You can yourself take a quiz and do a self-evaluation, or you can have a third party such as exida come in and evaluate your site safety to give you an unbiased viewpoint, and you will get a site safety index of 0 to 4. They're set up just like your safety integrity level. 0 meaning nothing. Repairs are not done, testing's not done, equipment's out in the field until it fails. You replace it and don't worry about it again. Hopefully nobody's in there, and every time I say that, somebody's like, we kind of are there. To Site Safety Index Level 4, where repairs are always done correctly, on time, testing is always done correctly and on time, equipment is always pulled before the end of useful life. Typically, we see people at a Site Safety Index Level 2, or if they're really good, Site Safety Index Level 3. And where this comes into play is it will affect how those dangerous undetected failures are either found or not found. So if you are that Site Safety Index Level 3 or 4, you can reduce your dangerous undetected failure rate, thus reducing your PFDavg, thus having a better risk reduction found. So I know I covered a lot, and we don't have much time left, but I'll stay and answer any questions. But we talked about functional safety, why it's important, what all it encompasses, how it started, how to put functional safety in operation, and then why maintenance and safety culture is so important to functional safety. As I said, I'm going to take some questions now. I'm going to go up here. If you think of questions later, please feel free to email me. I'll get to them as soon as I can. We're really busy right now, which is a great thing. But for more information, like I said, if you wanted more information on the other blogs or or other webinars, please see our website. We have blogs, webinars, white papers, books, all of that fun stuff. If you realize functional safety is now your passion and you want so much more, we have classes. FSE 100 being a full 4 days jammed packed full of functional safety. We have stuff for burner management, intro classes, and we have many more on the website. And if you think of any great topics or want more information, feel free to look us up. We have Twitter, Facebook, LinkedIn, or send any webinar topic ideas to exida, Academy at exida. We'll try and accommodate as many as we can. We have a question about cybersecurity. This is a great question. Should cybersecurity protection be applied to a SIS? Absolutely. Now that cybersecurity is becoming more and more of a threat, it's something that you need to be considering. And the standards are now encompassing it. The previous versions of the standard basically said, if you need to consider cybersecurity, consider it. If not, don't worry about it. Now it is actually being inserted into the functional safety life cycle, and it's being brought to the forefront of the next version of the standard. And so cybersecurity is something you definitely need to look more into. If you want some more information on cybersecurity, feel free to email me. I can show you a couple of good webinars, a couple of good blogs, and get you pointed in the right direction with that. Thank you so much for joining us this evening, and we hope that you enjoyed. Come back and see more exida webinars.